So I'm Sathasivam, and I'm a PMR fellow from ISET TVM. And my research area is actually in group theory. So if you want to contact me, you can contact me via the email ID. So, but here are some pictures of our institute. Okay. Anyway, so let's start. So the first question says the following. You want to determine which of the binary operations here are associated. Okay. So the first one says you have the set here is a Z is a set in which there is a binary operation defined as A star B is A minus B. So the question is whether it is associative. Okay. And similarly, the second question is the star is defined on R where A star B is A plus B plus AB. Okay. And whether this one is associative, and there is another one defined on Q. Okay. So I think the way that I plan to do the tutorial is like probably I will show the question and maybe I will introduce the question. Then I probably give you a few minutes to try. So in that time, you can understand the question and able to, if you can solve it, it's good. Okay. After a few minutes, probably I will tell the solution. And whenever you have doubts, you feel free to raise your hands and call me and ask the doubts. Okay. So you can try for a few minutes. Then I will probably start with the answers. Yeah, so you're telling option B and C are associative. Okay, I think somebody's telling option B and C are associative. Let's see it if it is true. Okay, let's start one by one. Let's look at the first one first. So the first operation is A star B is A minus B, right? So here A star B is nothing but A minus B. Okay. Now we want to check associative. That means we want to verify whether A star B star C, whether this is equal to A star B star C, right? So let's write here. What happens is A star B star C. This is nothing but A minus B star C. Okay. This is A minus B minus C. On the other hand, if we try that A star B star C, if we try this one, probably I'll just move a little bit. So this will be what? This will be A star B minus C, and this will be A minus B minus C. This will be A minus B plus C. Okay. So in general, these two things need not be equal. Okay. It can be equal at some time, but it's not always necessary that these two things are equal. Okay. So which tells you that the operation is not associative, right? So let me mark it as 1 and 2. So I can say from 1 and 2. Star is not associated. Okay. So for example, you can take A and B are 0. For example, if you want explicitly, you can take A equal to B equal to 0, and maybe take C as 1. Okay. So let's move on to, so this is not correct. So this is not associativity. Let's move on to the second one. So the second one is A star B is given by A plus B plus AB. Okay. So let's look at both of this. So this will be A plus B plus AB. So star C. So this will be A plus B plus AB plus C plus AC plus BC plus ABC. Okay. So you just apply the same thing here. You see it as a letter X, it is X star C, and then just apply that. Now let's look at the other one. A star B star C. This, if you look, it will be A star. So when you always evaluate the parenthesis first, right? So this will be B plus C plus BC. So now if you do that again, plus AB plus AC plus ABC. Okay. Now let's check everything is same in these two. Okay. So here is a, here is a, here is a B, here is B, C is also there. So we have AB here, AC here, and the BC is also here. ABC is there. So these two terms are actually equal. Okay. So let me call it some 3 and 4. So 3 equal to 4. So this implies the star is associative. Let's do the third one also. So this is correct. Let's do the third one. Okay, so the third problem, I think this is B, right? So A star B, this is defined on Q. How you define is A star B is A plus B by 5, I think. Yeah, this is correct. Now let's compute again the same thing. Let's compute. So A star B star C. If you compute what you will get A plus B by 5 star C. This is nothing but A plus B by 5 plus C by 5. So you can, this is A plus B plus 5C by 5. Let's compute the other one also. A star B star C. So this is B plus C by 5. Now when you compute, you will get A plus B plus C by 5 divided by 5. Okay. So what will this be? This will be 5A plus B, sorry, 5A plus B plus C divided by 5. Okay. So if you see here, the 5C is here, but let's say the 5 is here. So you can easily see, in general, these two equations need not be same. Is there any doubt?
Sir, in denominator 25.
Okay, thank you, thank you. Yeah, yeah, denominator will be 25. Yeah, thank you. So from 4 and 5, sorry, I think 5 and 6. So we get star is not associated. Okay. Okay. So this is a okay. So we have done which are the ones are associative. Let's take the same problem. Let me call the second problem here. So which of the above operations are commutative? Let's find. So commutative means recall commutative means A star B is equal to B star A. So let's go and try. So these are the three operations we have, and let's paste here just so that we know. Okay, let's check which of the following operation here are commutative. The first one is definitely not commutative, right? So let's do the first one. What is A star B? A star B is A minus B, and B star A is actually B minus A. And you can clearly see these are kind of the inverse of each other and they are not commutative. So what about the second one? So the second one, let's say A star B is actually A plus B plus AB. What is B star A? This is a B plus A plus BA. Okay. So is this commutative?
Yes.
Yeah. So because you are working with the R, right? The R elements are commutative. See here, if you look, this is a B plus A and A plus B, but in R you can commute this A and B. So since the addition is commutative in R, so you can write like this. And also multiplication is also commutative in real number. So you can write AB. In general, you cannot always write like that, but since you are working with a real number where these elements are commutative, so you can commute here. So this is commutative. Okay, let's look at the third one. So here the operation is A star B is A plus B by 5, and B star A is also is B plus A by 5. But again, you are working with the Q, where in Q A plus B is equal to B plus A. Right? So your operation is commutative again. Okay. Okay, so you can keep as an exercise. Try to find whether the identity and inverse exist. Okay, so that you can keep as an exercise. So for this same binary operations, but check whether so identity and inverse exist. Okay, let's move on to a different question. Here we have so the question is which of the following set is group under addition? So we are working with mostly we are working with a subset of rational numbers, and we are trying to see which of the following is a subgroup basically. Okay. Let's do one by one again. So the first one is the set of all rational numbers. Uh, so including 0, you can see 0 so 0 by 1. The lowest term whose denominator are odd. I think Sir has told what is the lowest term, right? For example, you have a rational number x, you can write it as 2 by 6. Okay, but this you can still cancel and you can make it 1 by 3. Okay, so this is a lowest term. I mean, this is a rational number expressed in lowest term, while this is not expressed in lowest term. So if you want to write abstract, lowest term means your rational number, let's say it is a p by q. By lowest term, we means that it is co-prime. Okay, so p and q, there is no common factor. So same as saying no common factor. Okay. So now the question is the set of all rational numbers in the lowest term whose denominator are odd. So basically this q is odd. So the question is whether this forms a group under addition. So let's try. So first what we have to do is we have to say it is closed under the addition, and then we have to go with associative, identity and inverse, right? So let's start to one by one. So first one is let's say closer, so closed under addition. So let's take two rational numbers. Let's take p by q plus r by s. Okay. So what we know is the q and r, these are odd. So if you add it, what you get is ps plus qr by qs. Okay. But here you should observe that this one, even though these two are in lowest form, this one need not to be in the lowest form. Okay. So right now we don't know what are the common factor. Let's say what are the common factor, we will divide the common factor and make it as the lowest form. Let's assume that. Okay, we can make it. So now the question is, once you reduce it into the lowest form, whether the denominator can it be even? That is a question. Because what we have to say is after we reduce to the lowest form, we have to say the denominator is odd. That is what we want to say. If we say the denominator is odd, then we can say it is closed under addition. So the question is after we reduce to the lowest form, whether the denominator is odd. So you can observe that q and s are odd, right? Since q and s are odd. So let me ask, does anybody has idea? Okay, let's proceed. So since q and s are odd, what we know is q times s is odd, right? So product of two odd numbers is odd number. Okay, so that is good. Now, if you look at, so when you change it into a lowest form, basically you are dividing some numbers, right? So whatever remains here will be a factor of qs. Okay. So Okay. So since QS is odd, what we can say is any factor of QS is odd. Okay, because 2 does not divide QS, and that means if you take any factor, 2 does not divide anyway. So any factor of QS is still odd. So now what we can observe is the denominator of this particular term, PS by plus QR by QS. So when you expressed the uh, this number as a lowest form, or maybe I will write a little bit differently. So usually we don't like to write like this. So maybe I'll erase everything. So let me write. So what is the number? When PS plus QR by QS, when this number is expressed lowest form. So what you can say about the denominator? So the denominator is a factor of QS. Okay. So we just see that any factor is odd. Since QS is odd, we just see any factor is odd. Okay. So now you use this fact that since QS is odd, any factor is odd. So if you use that fact, what you get is this odd, and this is odd. Okay. So that concludes the closure. Because we just want to say that the denominator is odd, right? When you express as lower term, the denominator is odd, but QS itself is odd. So any factor is also odd, and hence you are done. Is that clear, right? Okay, so let's move on. See, if it is not clear, you just let me know, so we can discuss. So now we have done the closure. So let's look at the other things also. So what is the second thing we need to do? The second thing we need to do is associative. So is this associative? Yeah, it is associative because Q is also associative. So see the addition here, this addition is the addition of rational number, right? So that's all. So in rational number, the addition is associative, and here also, so it is associative. So the addition of two rational number is, addition of rational numbers are associative. Okay. Now what is the identity? So identity is 0 by 1. So you can see that 1 is the, it's an odd factor. So it is odd. And what is the inverse? So inverse of, let's say, P by Q, where Q odd. The inverse is basically minus P by Q.
Excuse me, sir.
Yeah.
Sir, you write the addition of rational number is associative. Sir, it is true, but in the group we have given, the result in the denominator is odd. We have to prove this or not. In the,
No, See, you don't have to prove, because we already proved that it is closed under addition, right? Basically, see, once you take this and you write it, and then you express it as a lowest term, it became odd. See, okay, here I want to say, see, these two numbers are actually same. They are not different anyway. But we are just expressing, in order to see the expression, we are seeing it as in the lowest form. We are expressing in the lowest form so that we can work with it. But if you actually look, these two numbers are not different. These two numbers are same. So whether you write like this or write like this, the associative, it does not matter. Okay. So for associative, you want to say that a plus b plus c, this is equal to a plus b plus c, right? So whether you write like this or write like this, that doesn't matter for associative. But here we want to see something like the denominator has this value, etc. So that's why we want to go to the lowest term, because otherwise it doesn't make sense, because I can write like this also, right? So 2 by 6, I can write 4 by this. So in order to make this representation unique, we are going for the lowest term. Okay, because the x, when you write the rational number as a p by q, it need not to be unique. So to make it unique, that's why we are going for the lowest term. But it is still equal. So associative, there is no problem. Does I answer your question?
Sir, I have a question. I have a statement that, sir, the in the first part, the set of rational numbers in the lowest form whose denominator are odd. So this set is a subset of rational number,
Yeah, it is a
and it,
subset of rational number.
yes, yes. And in rational number, you said associativity is applicable. So every subset of a set which is applying as associativity is subset also applicable for associativity.
Yeah, that is true. So yeah, I think you got the idea. So that's a fact. If you want, I can generally state here, maybe towards the end. Suppose you have a set. Let's say, let the set. So let's say we have a set here. Let a comma star. Say b, a binary operation. So basically, the star is a binary operation. On a set, let's say a. Okay, and let's consider. Okay, probably I will write it as a star here. Let star. Suppose let's say we have another set. Suppose B is a subset of A, and let's say B is closed under the binary operation. So basically, if you take two elements in B, what I mean is, let's say you take B1, B2 belongs to B. What by closed I means B1 star B2. This also belongs to B. Okay, so that's what I mean by closed under binary operation. Then the associative and even commutativity, both of them. So we can say here I can write then B comma star. Okay, is commutative. I can write here associative also. Associative. If A comma star is commutative. So what I'm telling is, suppose if the bigger set is commutative, then the smaller set is also commutative. The same thing holds for associative. Because see, if you want to say something like a plus b, uh, let's say two element, let's say a comma b belongs to b, and you are looking at a plus b. Okay, so the question is whether this a plus b is equal to b plus a. Okay. See, now what we have is b is a subset of a, right? So at the end of the day, it doesn't matter because this a plus b here, it's here, but it is also here. So the operation here, operation of b is comes from the operation of a. So this element are equal in a, and hence it also has to be equal in b. Okay. So this is the same element in a, so it has to be same in b also. The same thing one can say for the associative also. So this is a kind of the general thing. Generally, you can say it. Okay, let's move on here. So if you have any other doubt, you can always stop me. Okay. So the inverse is again minus p by q. Okay. So this one is a group. So in fact, you can say this is a commutative group also. So in fact, you can say it is abelian group. Why abelian? Because q is abelian. So the same property holds for here also. Okay, so this is correct. But before proceed further, let's put a name for this sets. C, D, E. So maybe I will do a few of this and leave the some more to exercise because I have other problems which are kind of more interesting than this. So let me do one or two and probably leave the two or three for you guys to try. Okay. So let's try this one maybe. So this is a set of all rational number with absolute value less than or equal to 1. Okay. So whether this forms a group under addition. So we'll try the C now. The set of all rational number with the absolute value less than or equal to 1. Okay. So if you, so what do you think? Whether it forms a group or not? So let's check. Okay. So let's say you take two number. Let's say we took one and we took one. Okay. And if you add it, it became two, right? So this set, let me call the set as B. So you see, one and the one belongs to B. But if you add one plus one, this two does not belongs to B. Okay. So it is not even closed. So not closed. Okay. Okay. So this one is easy. So this is not correct. Oh, I need to call that as a C, but anyway. So let's try this one also, maybe. So this is a kind of the other way around. So it's a set of all rational number with absolute value greater than 1 together with a 0. Okay. So let's do that. So before that, I will just change the symbol here. This is C. C. So this D is a set of all rational numbers such that maybe you have to write with absolute value. And 0. Okay, so basically this union 0 is what we are taking. So is this a group?
No, sir.
And by the way, I think some people have messaged something. Please enlarge the font size. Okay. I'm not sure how to enlarge the font size. So this is already big, right? Maybe you can try to uh, change. I mean, you have to change from your side, I think. So, I mean, I can write big, but I mean, in some sense, it will only take, if I write something like that, I can write only very less amount here. So if you can resolve it, it's nice, it's good. Otherwise, let me know and let's see what we can do with that. Okay, so yeah. So as he said that it is not a group. So let's see why. For example, you take two number and see whether it is closed under operation. So let's take this one, 11 by 10. Okay. So this belongs to D because its absolute value is greater than 1. And let's take maybe 10 by 10. Okay, 10 by 10 is basically 1, right? So this also belongs to D. But let's look at, or maybe I take minus 10 by 10. Okay, so this is minus 1. So now let's look at 11 by 10 plus minus 10 by 10. Okay. So this is nothing but 1 by 10. See, this absolute value is less than 1. Okay. So thus D is not a group. Okay, so yeah, okay, maybe I can try this one. Let's see. I hope this might change a little bit, but we can only able to see so much, only able to write so much. That's why I don't want to keep it like this. But I hope you can. The font will be a little bit bigger, I think. No? Okay, let's move on to next problem. Here. So okay, now more or less. Okay, yeah, here I still haven't done much. So this is also not true. There are three more parts here, but you can keep the rest as exercise because we can move on to something interesting. Uh, so you can mail me if you cannot able to solve or you need some help. You can always ask me. Okay. So the rest I will keep it as exercise. Okay, they are not hard actually. If you try, these are all easy. Okay. So let's move into something a little bit more interesting here. But before that, I'll just look what is in there. We're talking about the print question. Oh, okay. Okay, that I can make it bigger if you want. Okay. Anyway, I keep the orientation also like this, but print question I can make it bigger, hopefully. Yeah, maybe that does not work. Okay. Okay. Just give me a minute. I think I screwed it up. Okay. So I hope you can see now. Okay. So this is actually there are two problems here. Let me just mark it as 1 and 2. So the first problem says the following: let X be element of group G. Uh, the prove that if the absolute, I mean, the order of x is n for some positive integer n, then x inverse is basically x power n minus 1. Okay. So what is the order? I think you might know, but I'll just recall, because this is the first class I will recall. So order of x belongs to G. So this is basically is the smallest integer, smallest positive integer. N such that it's identity. Okay. So here we are saying positive, not 0. N you cannot take as 0, because x power 0 is always defined as 1 for all x. So don't take a, you need a positive integer. Okay. Okay. So the question says that the order is n. Okay. So usually people write the order of x. On this n, people usually write as order of x is n. Okay. Or there are other notation like order of x, or people sometimes like order of x. This is also notation. This is equal to n. Okay, so these are notations. Okay. So now the question says the following. We know that the order is finite, right? So there's some positive integer. Now we want to say x inverse is basically x power n minus 1. Well, let's try to do it. So what we know is x power n is 1. Right. So what does it tells you? Let's write the x power n a little bit differently. X into x power n minus 1. Okay. So this is basically x power n, right? And this is equal to 1. So this is what it says. These are equivalent statement. So, but what does this mean? This means x inverse is basically this one. So this one is basically x inverse. Or if you want a little bit more rigorous, what we know is that this is equal to x inverse. Okay. So now use the cancellation property. Cancellation. Okay. Then what you get is x power n minus 1 is equal to x inverse. Okay. So that is exactly what you want. Just apply the cancellation property, you will get that. Let's look at the second problem. It says that let's say x and y are element of G. Prove that xy equal to yx. So basically it commutes if and only if y inverse xy is equal to x. So this type of thing are usually called as conjugation of x by y. Okay, so there is a name for it. And if and only if x inverse y inverse xy is 1. Okay. So let's write it one by one. So let's first prove the first one. First one says is xy equal to yx. If and only if I think y inverse xy equal to x. So how do you go there? So you take xy yx, right? So this is the claim. Let's prove it. Okay. Now what you do is just multiply both sides by y inverse. Okay, so y inverse xy. This is equal to y inverse yx. Okay. So I need to write. And of course I can change the brackets here. But let's leave the first one as it is. Xy is equal to y inverse y x. But this is just x, because this term will cancel out. This is equal to 1. So this is just x. Okay. Now let's prove the other one also. Maybe I'll just change the color. So other one what you want to prove is y inverse xy. This is equal to x. This implies and this implies x inverse y inverse xy is equal to 1. Right? I think that's correct. So how do you do that? Again, this is my claim. Let's prove similarly. Let's start with the y inverse xy. This is equal to x. Let's start here. Now multiply both side by x inverse. So x inverse y inverse xy. This is equal to x inverse x. But this is equal to 1. Okay. So there is nothing to write here. This will get cancelled out. These two numbers get killed and you will get 1. Okay. So this is a obvious, we just change it and you will get it. But I will just want to give one small remark before we proceed. So this symbols here, it is called, later you will study. Maybe if you do the group theory little bit more, you will study that this is usually denoted by xy. And it is called a commutator. So it's called the commutator of xy, x and y. So this is one of the very important object in group theory. Later, when you study group theory, and maybe not the first course, you may not do it in the first course, but when you do advanced group theory, this is one of the important object. So what this object tells you is, in some sense, it captures whether your group is a commuting group or not. So what this problem, if you look here, what this problem tells you is that your group is commuting. If let me call this as commutator xy. It says if your group is commuting, if the commutator is 1. Okay. So this elements, in some sense, if your group is not commuting, these elements will not be 1, and it in some sense captures how far your group are from being abelian. So abelian groups are kind of well understood. If your group is not abelian, it's hard to understand, and this commutator helps you to tell how far your group is from being abelian. Okay. So right now it's not necessary, but I just want to tell these elements are important. Although we write something here randomly, these are kind of important. These objects are important. Maybe we may not consider that in the first course, but yeah, later it will become very important objects. Okay, let's do this problem. So this problem is it is in the exercise. So the first one says GH inverse is nothing but H inverse G inverse. So when you take the inverse, it will not directly go like G inverse H inverse. This is not correct, but you have to change it the otherwise. Okay. So some people actually call this as if I'm right, I think they call it as okay, just give me 1 minute. Yeah, so uh, it's called as let's say Susak's lemma. Okay. So it's, you can kind of see it like that. Let's say this is a socks, and kind of see this is a shoe. Okay. So when you put shoe and socks in your leg, how do you do? Is you first put the socks, then you put the shoe, right? If you want to take out the shoe and socks again, what you do? You first take the shoe. So this is what happens. Let's call this as a shoe. So if you think this is kind of weird that order changes, you see it like that. And let's say call this a socks. Okay. So when you put in the leg, you first put the socks and then you put the shoe. But when you want to take out, you will not take out socks first, right? You will take out the shoe first. So you undo the shoe, then you undo the socks. So it's kind of the inversion, kind of the order changes. Okay. So if you ever, if it is confusing, you see it as some way that where we naturally do in the real world. Okay. So the what you have to prove is the inverse is basically this. So let's prove it. So how do you say something is inverse? I just have to say, see, we know that inverse is unique, right? That was one of the problem done in the lecture. Inverse, if it exists, it has to be unique. So let's prove that this satisfies the property of defining property of inverse. Okay. So we have to show GH, H inverse, G inverse is equal to 1. Suppose if you show this, what does it tells you? This tells you this is has to be the inverse. Well, this is obvious now. If you look here, this is G. You can change the brackets here. H inverse, G inverse. Okay. So maybe you have to change the brackets a little by little. Then you have to do that. Okay. So if you do that, what you will get is so first these two will go out. So you will get G inverse, and that also will cancel out. So you will get 1. Okay. So if you want to see how you to change the bracket, see from here, I changed the bracket something like this, right? Maybe this is the first time you're doing. I will probably tell you how to change the bracket. I mean, it's just associative. Associative means you can change the bracket whichever the way you want. But just for the, because you might see it for the first time, so let's change the bracket completely properly, because I just directly wrote it. But I feel that let's do it completely in full detail for the first time. Okay, so GH we have here, and H inverse, G inverse is what we have, right? So now you see this as a single element, okay, and this as two elements. Let's see this as some X, and this as two elements, okay. So this, if you see like that, then what happens? This is basically X, H inverse, G inverse, right? Now we change the bracket here. We change the bracket here, so maybe I'll just see it as a single element, maybe I'll say. And this one you see it as a two elements. Okay. So this is a GH. This is just one element, and then you will get a H inverse. Okay. And then G inverse. Okay. Now you do apply the associativity again. Okay. So this is a, see it as a two element now, and this is one element. So you can change the bracket here. This is nothing but G, H inverse, G inverse. Okay. Now these two will cancel out. So what you get is a G inverse, and this is equal to. Okay. So if you have associative, doesn't matter however the bracket you put, you can always change the bracket in whichever the way you want. But if you want the proof of it, then maybe you can check it in the book. Probably it is a little bit tedious, but you can prove it. Okay, so but here I just want to say, I'm just showing you, you can change the brackets. Just repeatedly use the associativity. You can change this brackets to this brackets. Okay. So although the problem looks easy, one has to actually change the bracket. If you are doing it for the first time, don't directly change like this. Go step by step and change the bracket completely. Then wherever you stop, you stop. Okay, let's do the second one. It says G inverse inverse is G. Okay. So these are all exercise in the lecture. So it says G inverse inverse is nothing but G. If you invert twice, you will end up getting the same G. Okay, how do you do that? So what is a G inverse in? So basically what you have to prove is G. Suppose let's look at this one. Okay. So what we know is G inverse is 1, right? Okay. This we know. But what does it tells you? It tells you this G is the inverse of G, right? Sorry, this G is the inverse of G inverse, which tells G is inverse, right? So that is same as telling G inverse is nothing but G. So there's nothing to prove here. Okay, so let's move on to a different question here. So I mean, the whatever we did earlier was kind of obvious, but this is a little more interesting. So here you take a G to be the set of all complex number such that z power n is equal to 1. Okay, so these are all complex number, like a complex number which has the finite order under multiplication. Okay, and this is a group, so we want to prove that this is a group under multiplication. Okay, and this group is called the root of unity because all these elements are basically nth root of unity. And then the second step is to prove that the G is not a group under addition. Under multiplication it's a group, but under addition it's not a group. So let's do A here. So I want to say that it's a group under addition, right? So let me take two elements. Let me call the Z1 and Z2 belongs to G. Okay. So what does it tells you? It tells you Z1 power N1 is 1 and Z2 power N2 is equal to 1 for some N1, belongs to Z plus. So Z plus means just it's basically a natural number. So now from here, how do you prove the closure? Let's start do one by one. So I want to say, let me first start with the closure. So how do you do the closure? So for closure, what I have to prove is I want to prove that Z1, Z2 power M is equal to 1 for some M. So this is my claim, right? So I want to prove that there exists a M such that Z1, Z2 power M is 1. Now the question is, what is that M? How do you find out the M? So any idea? Maybe this one, I will just wait for a few minutes, maybe 1 or 2 minutes. So you can have, you can think about it. So what we know is for Z1 and Z2, there are the N1 and N2, right? Now you're working with the product. For product, what has to be this? That's a natural choice here. Anyway, so I will tell. Uh, so you have to choose M in such a way that it works for both of them, right? So let's choose M to be just N1, N2. Okay. You can also choose it to be the LCM, but we can just choose it to be N1, N2. Okay. Now you look here, z1, z2 power n1, n2. Okay. This is basically z1 power n1, sorry, n1, n2 times z2 power n1, n2. See, you can split like that, provided your group is abelian. Okay. Here we are using the property that it is abelian. Otherwise, you cannot split like this. Okay. But anyway, I think I probably prove here. See, here I'm going to prove it here. So we will come back and prove this. So for now, let's assume this. Okay. But right now itself, we will prove it. Just 1 minute. There is one comment here. N1, N2 is also equal to 1. Yeah, that is correct. So it's not always true. For if you take a random group, let's say for example matrix group, this is not necessarily true. But as long as your elements commutes, you can separate it. Otherwise, see, if it is not commutes, you cannot separate, right? That's where the commutator comes into picture. It will be like a commutator AB power n choose 2, etc. It will come like this. So that is where the commutator is in some sense very important. Uh, but we don't care about that for now. As long as it commutes, we can do that. If it does not commute, there's a problem. But that people attack those kind of problems also. Later we can put a commutator and we can work with that. But let's not worry about that. Okay. Since your group is abelian, you can split. Okay. And this you can write it as z1 n1 power n2 times z2 n2 power n1. So this n1 and n2 also you can swap it. Okay, because these numbers are associative, right? This is a product in natural number, so this also you can swap it. Okay, so this is something like this. Okay, and we know that this is 1 and this is 1, so entirely it is 1. So it is 1 dot 1, which is 1. Okay, so here also I'm using some particular property, right? So I'm saying I can write this one as a product like this. Okay, so here I probably write it somewhere here. So here, this is the law of exponents here. So the law of exponents states that if you have x power a plus b, you can write it as xa plus xb. And if you have x power a power b, you can write it as x power ab. Okay, so this is also true that this is equal to x power ba. It is true. This is also equal to x power b power a. Okay, so this is true. And this is the second one, which says that if you take x power a inverse, this is nothing but x power minus a. Okay, this by definition, x power minus a is this. Okay. So I think x power minus 1 is defined, right? X power minus a is basically nothing but x inverse times x inverse times x inverse times something. Okay. So the problem says is if you take x power a, which is nothing but x times x times x, uh, a times. So this is a times. And if you take the inverse, this is same as taking x inverse a times. This is basically Susak's lemma. But proving that you have to go via induction. But for now, we will not do that. But let's assume that this property holds. In any group, this property holds. Okay, so this two properties you can say, but this AB you can choose from any integers. The first when you prove that, first you prove for positive numbers and then use this thing to prove for all the integers. But this is true for all integers. Okay, so that property we are using here. Okay, so here we are using the law of exponent. So never just multiply and swap it like that when you are doing the real number or like rational number, etc. Because most of the time things are not not commutative, so it's you cannot always just swap it. But this anyway, this law is satisfied for any group. So this is a law of exponent. So the first step we can do because it's abelian, and second step is law of exponent. Okay, so what we have proved is this is also belongs to 1. So that means this is closed. Okay, here. So this is the question. This is my group, and we just prove that the multiplication also there exists a m such that this is equal to 1. So that means z1 and z2 belongs to G. Okay. So closure is done. Okay. Now let's look at other things. Let's look at the second one. What is the second one? Associative. Let's look. Well, see, associativity is again easy because a complex number is associative. Okay, so we don't have to worry about associative much. So what is the identity? Identity is basically 1 because it's a group under multiplication, right? So 1 belongs to G. Why 1 belongs to G? Because 1 power 1 is basically 1. Okay, so 1 belongs to G. Since. So this symbol means this means since. So since. So the reason is 1 comma 1 belongs to 1. Okay. And what is the inverse? Okay. So you look here, what it says is some n star, right? Now you want to find what is the inverse. So let's think for a minute and see whether you can find it.
Z to the power n minus 1.
Z to the power
N minus 1.
Yeah, you are right. So inverse is basically what? Inverse is, so inverse of Z, right? Inverse of Z belongs to G. This is basically Z power n minus 1. Why? Because Z power n is equal to 1, right? For some n. So take that particular, well, okay, that is true, but you have to be little bit careful. Okay, let's do it a little bit more properly. Okay. So what we know is Z power n is equal to 1 for some n. Okay, so that means what we know is the order of Z is actually finite. So basically it means the order of Z exists. Okay. So let we say let m be the order of Z. It exists because for some n anyway it is has to be 1. So order is the smallest such number. So since there is a number, we can always look at the smallest such number. If any number does not exist, you may not always talk about the order. But since for some n, Z power n is 1, you can always look at the smallest such n, and that is the order. Okay. So now, what is the inverse? Inverse is basically, so inverse of the small z is basically Z power m minus 1. Okay. I think, probably you don't have to worry about the order. I think you're right. Even Z power n minus 1 will work. For some n, let's say it is Z power n is 1, then you can always take Z power n minus 1 as the inverse. So yeah, you don't have to do it anyway. Anyway, probably I'll just cancel it out. So maybe I'll write here like this. Z inverse, this is basically Z power n minus 1. So we just have proved it here, right? Just give me a minute. Yeah. Okay. So we just proved it. Okay. So that means G is a group under multiplication. So we have proved all the properties that is needed. So this G is a group under multiplication. Okay. Now let's look at the second one.
Sir.
Yeah.
Sir, if the order of Z is M, then z to the power m minus 1 and z to the power n minus 1 should be equal. Because inverse is unique.
Can you say again? Let's say if the order is m.
Yes, if the order of z is m,
Yeah.
then z to the power m minus 1 also is an inverse.
Yeah, they will be same. So
Yes.
have you studied the, yeah, that is true. They will be same. It doesn't matter however you write, they will be same. Have you studied this? What is that? Modular arithmetic.
No, sir.
Okay, okay. But anyway, we will do that later. When you do that, you can understand these numbers are actually same. It's the same as like we have this, right? 1/2 is also same as 2/4.
Yes, yes.
So it's kind of like that. But later you will understand. So see, if you look at this construction, you can see it's a similar kind of construction. So you will define equivalence relation, partition, and those kind of things. But let's not worry about right now. But you're right. These two elements will become the same. After a while, it became the same. For example, here we can do like that. Let's say z power m is equal to 1. Let us have it. Okay. So what happens to z power m plus 1? This will be equal to z, right? So these numbers will become kind of the same. So you can see it like this. So let's say you have 5 elements here. What you do is when you multiply this element with the same element, let's say call this as z. Okay, and this is z square. This is z cube. This is z power 4, z power 5, z power 6. And then this became z power 7. This became z power 8, z power 9, 10, 11. It goes like this in some sense. So later you will study that. These kind of groups are called the cyclic groups. You will study it later. Okay. So what we have done is we have proved that it is a group under multiplication. So this much is done. So now the claim is it is not a group under addition. So can some of you figure out what property is not true? And if it is not true, can you come up with an example? Maybe you take a few minutes, it's fine. As long as you can able to think on the spot, it's good.
Sir, it's not closed under addition.
Yeah, that is true. So there are many things you can say. For example, it is not closed under addition. You can say even the identity does not exist. Okay, if it is closed, yeah. So the identity has to be 0 if you think about it, but the identity will not exist, etc. But the easier one is to just say it is not closed under addition. So do you want to explain why? Okay. Otherwise, I will tell why. So let's take two element, and I want to say it is the addition is not there, right? So you took one. Okay, one belongs to the G, and minus one also belongs to G. Why? Minus one square is actually one, so minus one also belongs to G. But if you look at 1 plus minus 1, this does not belongs to G. This is equal to 0. This does not belongs to G. Why 0 does not belongs to G? Whatever n you take, 0 power n is actually 0. This is not equal to 1 for any n belongs to n. Okay. So, okay, I need to write a bracket here. Okay. So what you have is the addition is not closed. So this is not a group. So G is not a group under addition. Okay, let's proceed to the next one. Okay, first let's prove this one first. This is more interesting. See, in order to say abelian, this is kind of like a characterization. Okay, so that if x squared is 1 for all. Okay, this is not a characterization. This is this is some statement. So let's prove the second one first. We'll come back to first one. We have to use the induction to prove it, but let's do the second one first. So the second one says if x square is equal to 1 for all x in G, then G is abelian. So if you think, how do you proceed? For the abelian, what we want to prove is you want to prove that xy equal to yx, right? This is what I want to prove. But what I know is x square is equal to 1 for all x. Okay, so let's do it here. So what you have to do is you have to choose this element. You have to find out what the element here you have to put such a way that it will become correct. Okay, so that is what you want to find. You want to find out a correct element to put here so that you can get it. Okay. So let's do here. Let's took xy here. Okay. Let's say what we know is xy square is equal to 1, right? This we know. What does this tells you? This tells you xy, xy, right? Xy, this is equal to 1. Okay. Now what does this tells you? It tells you xy is equal to, because I can now we multiply by y inverse first on both sides and then multiply x inverse on both sides. Okay. So if you multiply, what you get it is y inverse x inverse. Okay, but I need it is equal to yx. So what to do now? So if you figure out what to do, then it's nice. You have already seen this already.
Sir, from the question, we can say that x is the inverse of itself because
Yeah,
x
that's
square
right.
is equal to 1. 1 is the identity, right? So then y inverse, x inverse should be equal to yx.
Yeah, that's all. You're right. So from here, x square is equal to 1, right? So that means x power 2 minus 1, which is x itself. This is equal to 1. So this is the identity. Sorry. Yeah. This has to be the x inverse, but this is nothing but x. So basically, it has the self inverse. Okay. So this is y. This is x. Why? Because x inverse is basically x. So that's all. It says that G is abelian. Thus G is abelian. Anyway, I think today every problem is a little bit easy. But hopefully in a few days we'll do a little bit more interesting. Okay, let's look at the second one. It says that, sir, let's do the first one. It says A and B are commuting element. Then prove that A B power n is A power n B power n. Okay. So let's write the statement. First one. If A comma B commutes, then A B power n is equal to A power n B power n. So let's prove that for 2 first. So okay, let's do the, see, when we are doing something by induction, something n which holds for all n, then we always go with index n, right? So that was a standard technique, and here also we use index n. Okay, so the base case is n equal to 1, right? So n equal to 1, what we have is ab power 1. This is nothing but ab. This is equal to a power 1 and b power 1. So this is same as telling ab equal to ab, right? So this is trivially true. So okay, so this is trivially true. There is nothing to prove here. So let's do n equal to 2 case also, just to get idea of what is happening. So here you have ab square. This is what? This is ab. But what you can observe is a and b commutes, right? So you have to change the brackets again and again and again. But let's do like that. ab. So this is a. So see it as a 2 element, see it as a 1 element. So this you see at a single element, and see it as a 2 element. Okay. So you see like this x ab. Okay. And you are changing into xa, that xa b. So this is what I am doing, and here you have b. Okay. And again you change the bracket a, ba, b. So this is nothing but a. So ba, now a and b commutes. So this element you can change into ab. B. Sorry, ab. B. Now commute it again. Sorry, use the associative again. A, b, b. So this is a square b, b. Now do it again. So a square, b square. So a square, bb. Nothing but a square, b square. Okay. So you have to change the bracket, use the associativity again and again, and one place you are using the commutativity. See, that is why he's telling. So in the book, it's telling you to do by the indexing. Okay, because if you are not going by indexing, there are so many brackets to change. The problem is it's not hard, but you just have to change so many brackets. So in general, doing that is not possible. That's why you are going by indexing. Okay. So let's do by indexing. So inductive hypothesis. So let's assume a power n, sorry, ab power n. Yeah, I'll write here ab power n is equal to a power n b power n. Okay. Now we prove for so we now probably I will write k here rather than n. So we prove for n equal to k plus 1. Okay. So let's do ab power k plus 1. So let's start here. Again, we have to do the same thing here. So ab power k. Okay. And we have ab. Okay. Now ab power k by inductive hypothesis, I can write it as a power k, b power k, ab. So this is the brackets you are changing are the same like whatever we did for 2. The same kind of changing you have to do. This will be like see it as a single element, see it as a double element, or you can do the other way around also, but it doesn't matter. This is a power k, b power k, a, b. No, I think this is not correct. Wait. Okay. And then change the brackets again. I think. Okay. So now you can use the commutativity. So this is A power K, A, B power K, B, B. Now again use the associativity A power K, A, B power K, B. Now I think I'll just write directly. I think at this point you might know what to do. So just combine these two and use the associativity again, you'll get this. Okay, so now by induction we proved it is so basically what is proved is P of K, the truth of K implies truth of K plus 1. Okay, what is the P of K? P of K is basically this statement. So P of K is the statement here. AB by K is equal to A by K. Okay. So now by induction the proof follows. That's all. Induction, the proof follows. Okay. Okay. So this we have done it. So let's go and do the other ones. So there are two more problems I have, and hopefully we can easily finish it. If there is more time, I can do other problem. So probably now you can tell me, since we have done for already for 1.5 hours, what do you think? Is it the pace is slow or fast? If you want little bit fast, you can tell, because it's a first class also, so I'm going a little bit slow. And also, I think it's better if all of us understand. So, but if you want some modification or feedback, you always let me know. Okay, so let's do this one, 26. So here the question says, assume H is a non-empty subset of G star. So G is a group and H is a subset of G, which is closed under binary operation on G, and it is closed under inverse also. Okay, so basically if you have two elements of H, Hk belongs to H and H inverse belongs to H. Now what you have to prove? You prove H is the group under operation star restricted to H. So this operation star is a operation of G. What it says is if you restrict the operation star to H, H forms a group. Okay, so that is same as telling H is a subgroup. So what it tells is in order to prove that something is a subgroup, it is enough to prove that Hk and H inverse belongs to H. So in some sense what it says is we don't have to check. So we don't have to check associative and identity. Okay, so that is what it tells you. Okay, so let's prove it here. So first one, closure, it's correct because of the hypothesis, by hypothesis. And what about the associative? So associative is true in G itself, right? So star is associative. Okay, probably the spelling is wrong. Associative in G. So in particular, it is associative in H. Thus, okay. So now let's come to the interesting one, identity. Okay. So let's say one is the, or probably I'll write E. Okay, E belongs to G is identity. Let's say. Okay. Now how do I say that E belongs to H also? So here is where the non-emptiness come into picture. Okay, since H is non-empty. Sorry. Okay. So there exists a small h. H belongs to H. Okay. So it's non-empty, so we can always choose one element. Okay. Now, since H belongs to H and this set is closed under inverse, what you can say is H inverse also belongs to H. Okay. We also have why H inverse belongs to H? Because the H is closed under inverse, right? So that was it's closed under inverse. And also it is closed under binary operation. Thus H inverse also belongs to H. Okay. What is H inverse? H inverse is basically just nothing but E. Okay. So thus identity also belongs to H. See, here is one remark I want to say. So let me put a remark here. Suppose G is a group, okay? So, because I hope, I mean, some of you may not have done like a logic course, like a rigorous logic course. Otherwise, it is what I'm saying is trivial thing. But I just want to make the remark. See, when I say the identity, the axiom of identity is what? The axiom of identity says the following: there exists one belongs to G, or E belongs to G. Some symbol they put here, such that 1 times G is equal to G times 1 is equal to G, right? So this is the identity axiom says. So what it implies is that the existence of 1 belongs to G. So there is always a element 1 which belongs to G. So G cannot be non-empty. Okay. So suppose G is a group, then G cannot be empty. Okay. So that is a problem. So that is why we are also assume that H is non-empty. Suppose if H is empty, then I cannot do any of this, right? Okay. So this is one is a very trivial thing, because for example identity, if you look what identity, sorry, what inverse says, inverse says for all. So let me write the inverse axiom also here. See what inverse axiom says. So this symbol means for all. Okay. Maybe I write directly here. So for every G belongs to G, there exists, let's say, H belongs to G, such that GH equal to HG equal to 1. Okay, usually we call this H as G inverse. We call H as G inverse. So G inverse is just any element such that GH and HG equal to 1. But if you look here, what it says is for every G in G. Okay, so this does not, this statement does not imply that G is non-empty, because even if a G is empty, what it says is even if G is empty, you take any G in G, there exists a H. Even in empty set, the statement holds. But this statement by itself says that G is a non-empty. That's why whenever somebody writes, they never write let G be a non-empty set. And then you are not defining a group, right? So if you look at the definition of the group, you don't have to define a group as a non-empty set. So you can start with any set, but the identity axiom itself tells that G is non-empty. So G is non-empty is a consequence. You don't have to write. Maybe some people start as a let G not equal to G non-empty be a set, and then you put a binary operation. Some people write like that. But you don't have to write like that, because the identity axiom says that G is non-empty. Okay, anyway, so we have proved the identity. So what about the inverse? Okay. So let me write here inverse. Okay, so yeah. So this statement always hold whether it's empty also, doesn't matter. But in empty state, see, for example, if let's say G is empty, then what happens to this statement? This statement says for every G in empty set, there exists H. See, but there is no G in empty set, right? So this part is a false. Okay. So this is a implication statement Okay, so what it says for every G in C implies there exists something. So this is the implication statement, and this step is false. So this statement is vaciously true. Anyway, let's move on to next one. So inverse by hypothesis. Okay. So why? So hypothesis says it's closed under inverses and binary operation. Okay. So we have proved all other properties. So it's a subgroup. So H is a group by itself, and such a subsets are called subgroups. Thus H is a group. Okay. Okay. In fact, if G is commutative, we can also say H is also commutative. That is, you can say. So same like the associative, we can also do the other one. Okay. So let's do this one also. So if there exists, okay, let's do the 27. I hope it is visible, hopefully. Okay, so what it tells is prove that if X is an element of G, then X power N, okay, where N belongs to Z, is a subgroup. So that is what it says. And this subgroup is called the cyclic subgroup generated by X. Okay, so let's prove it. So by the previous exercise, all what we have to do, we have to prove that, look at the previous exercise. It says in order to prove something is a subgroup, it's enough to prove that it is closed under the binary operation and the inversion, right? So let's just do that much. Okay. Okay. So how do you prove binary operation? So first one. So let's prove one by one. Okay. Let's prove binary operation first. So let's say x power n, comma x power m belongs to whatever the set is. Let me call the set as G. Okay. Belongs to G. So I want to claim. Oh, so that is not G because there is already G here. So I probably call it a C. C stands for cyclic. Let's say belongs to C. So first, what we have to prove? We have to prove x power n plus m. This also belongs to C. Okay, how do you prove that? Not x power m plus m. You want to say x power n times x power m also belongs to C. Okay, this is the claim. But you see, x power n times x power m, you use this law of exponents. Okay, this is nothing but x power n plus m. Okay, and this belongs to C, right? Because n plus m also is an element of integer, so this belongs to C. So closure is done. So done. Now let's do the inverse. Okay. So inverse also you do the like similarly. So how do you prove the inverse? So let's say x power n belongs to C. Now what is the inverse of this? Inverse of this is basically x power minus n. Since n belongs to integer, minus n also belongs to integer. So what is so x power minus n? Let's take. So what is x power minus n? X power minus n. So here you go here. So x power minus n is basically, okay, by definition this is nothing but inverse x power inverse times n times. Okay. So this is by definition. But we know that this is nothing but it is equal to x power minus 1 power n. Okay. So we can write like that. So my claim is x power minus n is the inverse. Okay. Well, I think you can directly do it. You don't have to worry about that. Probably I will do two proof. I mean, both of them are the same, but I just do it just so that you can see. One is you take x power n and x power minus n, apply the law, apply this law. So this is nothing but a plus b. See here, the third part says this is true for a and b. It can be positive, negative, or zero. Doesn't matter. Okay. So one of that is positive, one of that is negative. You apply it here. What you get here, you will get n minus n. So this is x power 0. So x power 0 is defined as 1, right? It is defined as identity. So that we have. So this is one way you can do it. Another way is you write x power n times x power minus n. So this is the same as x power n times x power minus 1 power n. Okay, so that is the second part. You can use the second part. Then see, observe that the x and x commutes, right? So x commutes with itself. So we can write this as the x times minus x, sorry, x times x inverse power n. So this is 1 power n, which is 1. So the same problem, there are many ways you can do, just how you want to do it. Anyway, so what we have proved is x inverse. So what we have proved is the following. We proved x power minus n is inverse of x power n. Okay, so x power minus n by definition is basically x inverse. So n times you multiply. Okay. Okay, so we have proved both of that. So we have proved it's closed under it's closer, and we have proved the inverse also. So that means inverse is also done. So by the previous test, by previous let's say by previous problem, C is a subgroup. Okay. So these subgroups are usually called cyclic subgroup generated by this particular element X. Okay. So later you will study what is cyclic group. Then you can understand why this is same as is called as a cyclic subgroup. Because if you look, this group will become a cyclic subgroup. So this subgroup is itself a cyclic group, and that's why it's called cyclic subgroup. Later you will study what is a cyclic group. So that time it will be more clear. Okay. So I think more or less, okay, let's do this one. So this particular one I will leave for now, because you see, you just have to use the induction multiple times. It became very tedious, but I'm not sure by doing that whether we learn anything new, that I don't know. Probably you can learn how to use the induction. Other than that, I don't know. So this part I'll just assume for now. Let's prove this one, but okay. So let me prove the second one. So what it says is for let's say x be an element in G, so that the x and x inverse have the same order. Okay, so let's do the second one. So the second one says the order of x is same as the order of x inverse. So you can maybe if you have any idea. So let's for now let's assume that order of x, let's say is n less than infinity. Let's assume the order exists. Okay. It is possible that there is no such n such that x power n is 1. Okay. You just have to use the law of this. Yeah. So what you want to find? You want to find the order of x inverse, right? So this, by definition, this is equal to, this is definition, x power minus 1 power a. Okay, so if you have any idea, you can tell, otherwise I will give the proof. See, what I know is the order is n, so what I know is x power n is actually equal to 1, right? Now let's look at, so I want to find what is the order of x power minus 1. Okay, let's look at x power minus n power n. Let me took this one. Okay. And if you take this, what we will have here? So this is nothing but what? This is equal to x power minus n. Okay. So what is x power minus n? This is x power n power minus 1, right? I'm using this law of large number. So the inverse, I can take the n up and then I can put the inverse. So what is x power n? This is 1 power minus 1. What is the inverse of 1? This is nothing but 1. So both has the same order, provided if the order exists. Okay. Suppose if the order does not exist, suppose order of x is, let's say, infinity. Okay. Then what happens? Then x inverse also, the order of x inverse also has to be infinity. Why? Suppose if x inverse order is not infinity, okay? Why? So let me write here y, and we'll give the reason here. Suppose order of x inverse is, let's say, some n for some n. Okay. Then by the previously whatever we done here, what you can say is, then okay, then like before. So like whatever we have done before, what you have is order of x inverse is n. But x inverse is what? It is basically x. Order of x is n. So that is a contradiction. Okay, because we assume that x has infinite order. So x inverse also has to be infinite. Okay, so now I have another question. Can you tell me at least one example where x inverse has infinite order? Sorry, where x has infinite order? Is there a group in which there is an element which has infinite order? So write a question here.
Can you repeat the question, sir?
Yeah. So see here, what I did is I assumed that order. I mean, because we are dealing two cases. One is the order of x is n. Another case is the order of x is infinity, right? So the question is, are there a group in which there is an element which has an infinite order? So the order of element can be infinite. Is there any group in which element has an infinite order?
So the set of real numbers
Under which operation?
under addition.
And which element has the infinite order?
Here 0 is the identity element.
Yeah, 0 is the identity element, but 0 order is actually 1, right? So 0 power 1 is actually equal to 0. Sorry. Yeah. So order of 0 is 1.
Sir, under multiplication, identity would be 1, and 0, how many ever times we multiply by 0, it won't give us 1.
Yeah, whenever you take, okay, here, that is one interesting thing. So if you take R and the star, okay, this is not a group. Why?
0, the inverse of 0 doesn't exist.
Exactly. because 0 times any x is 0, and thus inverse 0 inverse does not exist. So 0 has no inverse here. So, but one example you can easily give, that's the simplest group that you know. So if you look at the lecture, what is the first example sir give to motivate you? Maybe one of the first example, maybe not the first. So let's took, see, there is a saying that like the God gives a natural number and the rest of the mathematics is made by man. So anyway, sorry, you take the integers, let's say, okay, under addition. So this is a group, right? Now let's look at the order of 1. Okay. So what is the order of 1? So the order of 1 is the smallest n, such that what we have 1 plus 1 plus n times, okay, 1. So basically this is equal to n times 1, which is basically 1, okay, or maybe it is just n is 0. Okay, is there such n exist? So the order of 1 is the smallest n, basically smallest n belongs to natural number, such that 1 plus 1 plus 1, like n times if you do, it has to be n times is 0. Okay, so that if such a n exists, that means n equal to 0, right? If order of 1 is, let's say, n, then what we have is n is equal to 0. Why? Because 1 plus 1 plus 1 n times is just n. So that tells you, because in natural number every n is none of these elements are 0, right? So the order actually does not exist. Okay, there is no such n exist, so we say okay, the order is infinite. So okay, thus order of 1 is infinite. Okay. So the simplest example that you know, you see, the order does not exist. Okay, so anyway, we will, since we talk about these things, let's do ask us the natural question that comes up next, which is, I was not preparing these questions, but you see, since we are doing with that order can be infinite. So the question naturally that comes is, so when the order exists? So the question is, so when order of x is less than infinity. So when order of x is finite. So at least a sub question of that is, so okay, this we may not able to say when order of x is infinite, because that depends on the group. Okay, so suppose you have a finite group, let's say, I'll change the question here. Suppose order of G is n. So what is order of G? It's the number of elements of G. Order of a group is basically the number of elements in the group. Okay, and then, and okay, maybe and let x belongs to G. Okay, so the question is, does order of x is finite? See, because we are working with a finite group, right? In a finite group, does every element has a finite order? That seems reasonable, right? And it is actually true. In a finite group, every element has a finite order. So how do you do that? So let's consider this is a cyclic subgroup generated by x. Okay, so let's consider x square. Okay, so maybe So x power 0, which is identity, consider x square, x cube, etc. Okay. So now there are infinitely many terms here, right? All of them belongs to G. So all of this thing is a subset of G. But my G has only finitely many elements, right? That means not all of them cannot be same. So not all of them cannot be different. It's the pigeonhole principle. So basically you have n boxes, so n elements you have. So this is x, this is the identity. This x is will be there, and let's say x square, x cube, etc. But there are only 4 boxes, right? So that means that the fourth element has to be here, or it has to be one of that. I don't know where it is, but it has to be one of that, right? It's just a pigeonhole principle. So since you have only finitely many elements, but you have infinitely many this x power n's, not all of them can be same. So thus x power n equal to x power m for some n comma m belongs to n. Okay. So without loss of generality, assume that n is greater than m. Okay. If n is not greater than m, then for some n comma m, so for some n comma m belongs to n. Also, what we have is n is not equal to m. Okay. So there are 2 different elements here, but they are equal. Okay. So that means either n greater than or equal to m, or n is less than m, or n is equal to m. So we are assumed this is not a possibility. So one of them is true. So without loss of generality, assume that n greater than or equal to m. Okay. Assume. Then if you look at x power n, okay, times you put x power m inverse on the both side. Okay, so this will become 1. Here, if you look, you use this law of exponents. So use this property. So you can write like this, okay? So if you use that property, what you will get here? You will get x power n. Okay, x power minus m is equal to 1. So that means x power n minus m is equal to 1. Okay, so that means the order exists. That's all. So that means for some n minus m, this is equal to 1. So you can always choose the smallest one, because the set is non-empty, like the set of all k such that x power k is equal to 1. So set of all k such that, okay, I have to write like that. Set of all k belongs to n such that x power k is equal to 1. This set is non-empty, so I can always choose the smallest one, right? That's a well-ordering principle. Using well-ordering principle, you can choose it. I mean, if you don't know well-ordering principle, doesn't matter. What it says is, if you take a subset of natural number, there is always the least number exists. So that is obvious statement. So you can always choose the smallest one. So that means the order of x exists. Okay, order of x exists. Okay. By exist, I means the order of x belongs to a natural number. Okay, so see, x is a element of a group, but order of x is a number. This number belongs to natural number. It is not infinite. That is what I mean. So again, there is a natural question comes. See, there is something like order of G, order of a group I have, and order of a element I have. Okay, what I said is, if order of G is n, then order of x is, sorry, if order of G is finite, then what I said is order of x is also finite. Okay, so can I say order of x in terms of this n? Can I say, is there any relation between order of x and the order of G? So that is another question that comes, because here we do some kind of pigeonhole principle, etc. So one may think there may be some relation, and in fact there is a relation. So the relation is, it's a theorem. Anyway, we are not going to prove now. I'm just motivating what is going to come. Lagrange theorem. So Lagrange theorem says this order of X divides order of the group. Okay. In fact, it says something more. It says if H is a subgroup of G, then the order of H divides order of G. Okay. So in fact, there is a relation between the order of element and the order of the group. Okay. Anyway, this will come later. It's one of the main theorem of this course, and it will be useful almost everywhere. I mean, at least in the first course, it will be very useful. So I just want to motivate that, and probably it will come little later. It will not come anytime soon. But right now, what you can assume is if a group has a finite order, like if the element in the group is finite, then every element has a finite order. But if the group has infinite order, one can prove the contrapositive of this statement tells you that. So this is also the truth. Okay, I will just write a fact. You can keep it as exercise. Okay, if the order of G is infinite, that means it is not finite. By infinite, I means it is not finite. Okay, then okay, this I think cannot say. Okay, this is not true. This is not true. Okay. Anyway, I will just write it. So again, I write as a question here. Suppose order of G is infinite. Does that exist X belongs to G such that order of X is infinite? Okay. So what we said here is if order of G is finite, then order of every element is finite. So here we are asking like the contrapositive of that. So not contrapositive. Here we are asking if suppose if it is infinite, does every element has infinite order? So this is a question, and the answer is no. But if possible, you can try to come up with a group. It may take a while to come up. Later we can prove once you then what is the direct product of group, we can easily prove it. But right now I am not telling. The answer is no, but you can think about it. Okay, then probably we'll stop now. If you have any doubts, you can ask me.
Sir,
Yeah.
in question number 27, we have proved that the inverse of x to the power m is x to the power minus m.
X to the power, can you say again? Inverse of?
Question number 27.
27, right?
Yes. Yes, here we have proved that the inverse of x to the power m is x to the power minus m.
Yeah, okay, yeah. You have proved it. Yeah.
So we prove that x to the power minus n is unique.
Yeah, it is unique. I mean, see, what happens is, how do you say, if you take a square also, let's say n times, right? Here you took another few times you took. Again, another n times you took. Okay. This is also, just give me a minute. Okay. So why do you think it is not unique? See, it is always unique. Inverse is always unique because you know about the cancellation. But anyway, you can say what you think. Then probably I can specifically answer it. So, okay. Anyway, I will tell something. You let me know if it answer your question. Okay. So let's say you have a element here. Let's say x. Okay. So all the real number, etc. What happens is you can easily see that number is unique. But sometimes what happens in a finite group when you work with, it is possible that, for example, this number and this number, okay, this can be same. Okay, it is possible. And in such a case, what happens is one may think, let's say, see, yeah, what one can think is, okay, these numbers are different. So there can be multiple inverses there. You can think like that, but actually what happens is these two elements will be the same, and hence the inverse by element itself is unique. So basically the element is there, but it can have a different representation, it can have a different expression, but the element will be the same. So once you land the cyclic group, it became more or less clear what happens. So that's what I said here. So there can be a group which goes like this. For example, this is 1, 2, 3, 4, 5. Okay. So let's say this is x to the power 0, which is identity, and this is x square, x cube, x power 4. And now the x power 5 can become identity again. So this became x power 6. So these elements are equal. So maybe let's say the inverse is x power 4, right? So you have x inverse is basically x power 4, because x power 5 is identity. But if you look here, this x power 4 is also equal to x power, I think, 9, right? This is x power 8, this is x power 9. So one may think these elements are x power 4 is also inverse, x power 9 is also inverse, but they are the same elements. So as a element, they are same, but it can have different ways you can write it, but just the same element. Okay. So once you do the cyclic group, you can understand it. That is why it is called cyclic group, because it goes in a cycle. So it's called cyclic group. Anyway, that I think it will come just in the next lecture. It will come. Okay. So if you understand it, you let me know. Otherwise, also you can try to specify the problem. Probably I'll try to answer it again. Okay, so probably I'll just assume that you understand. So yeah, so we can meet in the next week. But if you still have the problem, you let me know. Okay. Okay. Anyway, see you later. Bye.
Thank you, sir.
Yeah. Thank you. Bye.
Thank you.